Applications Engineer at LDRA, and today I'm here to talk about functional safety and security in systems. So first of all, let's talk about what is functional safety. Well, functional safety is part of the overall safety of a system or piece of equipment that depends on automatic protection systems. And this automatic protection system needs to be able to respond correctly to its inputs. And it should also have predictable responses to failures. So this includes errors such as human errors, hardware failures, and operational or environmental stress. And so safety standards were designed to ensure that this happens. But they often come with complex requirements for software developers. These safety standards ensure that we all have our bases covered, so that inputs lead to desired outputs, and that any erroneous inputs and failures are predictable and known about. Now, there's an increasing demand for Qt-based GUI applications in the safety critical sectors, such as the industrial, medical, and automotive sectors. And so the need for this functional safety is increasing. And as such, safety standards are developed for these very reasons. For example, we have IEC 61508 for the industrial sector, IEC 62304 for medical, and ISO 26262 for automotive. Now, many of you might have heard of an incident from a while ago where cars produced by Toyota would unintentionally accelerate, and it resulted in a loss of life and injuries, a $1.2 billion fine, and other damages. Another more recent example would be the Boeing 737 MAX 8 incidents, which I'm sure everyone has heard about. And these are just some of the examples among the many that you'll hear about in the news. But they serve to highlight the need for functional safety in the safety critical sectors. However, the process for getting certified requires a lot of effort and can be very time consuming. So I'm going to go over some of the challenges of becoming compliant with functional safety and getting certified. First of all, we have requirements and traceability. Building a complete set of requirements for the system is the first step. If requirements aren't documented, you aren't going to be able to test against those requirements, and therefore you won't be able to provide evidence that the system is meant for its intended purposes. And traceability is needed because it helps by showing that requirements can be implemented and tested. Next, we're going to need to be compliant to coding standards. Following a coding standard is a required process in almost every functional safety process standard, if not all. What's the reasoning for this? Well, for one thing, it makes sure that your code is consistent and readable. It significantly reduces the likelihood of introducing bugs and defects that could have been easily avoided, like buffer overflows and divide by zero errors. Another thing is that it also reduces the time spent manually debugging code in the future when an issue is identified later on. The next thing we need to take into consideration is code complexity. How complex is your code? Often, complexity in software is managed through a coding standard. With a coding standard like MISRA C 2012, complexity management is more of a supplement because the undefined behavior in C is something that MISRA helps programmers to avoid. But complexity can only be managed within the context of this project, since different projects have different complexity requirements. If your code is too complex, there's a higher chance of it becoming vulnerable to errors. And with low code complexity, it becomes a lot easier to understand your code, making it easier to develop and unit test code. It's also going to be much more efficient to work on. For data flow and control flow, we need to take into consideration how each component of the software interacts with each other. and if they are reliant on other components of the software. We also need to be aware of how the components in the software will rely on data objects from within the system. Structural coverage is also really important when it comes to functional safety. When performing requirements-based testing, you can use structural coverage to check if testing is complete. If all your tests have been run, and since all tests should be traceable to requirements, you should see that you have 100% structural coverage in your code. Now, if you have code that isn't covered, you have to ask yourself, why is this code here? Is there a gap in our requirements, or is this dead code? In which case, it needs to be removed. And next, we have target integration testing. Tests by themselves are great, but they're kind of meaningless unless they're run from within the same environment as the final system. It doesn't really make sense to claim certification credit on tests that are run in a different environment. For example, using GCC on Windows for code that's meant to be run on a Linux target. And so this means using the same compiler and environment as the shipped final product. Tool qualification is also an important thing to consider. How can you be sure that the tool is doing exactly what it's expected to do? You'll need to qualify or test the tools to make sure the results you're getting are correct. And finally, there's compliance management, which requires the generation and management of project documentation, reports, artifacts, etc. And this is necessary to establish a chain of custody and make sure that everything is documented and accounted for. And once all these requirements are met, your software can be certified for the safety standard you're using. This is what's called a V model. For safety requirements, for functional safety standards, building a set of requirements into a V model is typically suggested or required. Requirements on the left-hand side can be presented with the associated level of tests on the right-hand side. The system-level requirements come from higher-level business rationales for undertaking the project, and often comes from the customer. Then, when the high-level requirements are written, they detail the requirements at the software and hardware level. The low-level requirements can then be constructed based on the software implementation needed. So once you have your requirements, traceability gives you the answers to the following questions. Does each requirement have an associated test? Does each test reflect at least one requirement? Is every requirement at a level, for example, a high-level requirement, is it covered by a low-level requirement? Requirements documents are also needed for traceability, and they come in all kinds of formats. Some requirement management tools are designed specifically to address the traceability challenges for safety critical projects. And here are some examples of the requirements management tools that LDRA customers use to write and manage their requirements. We have Codebeamer, JAMA, Polarian, and sometimes even Excel. Traceability is the linking of all these artifacts together to create a coherent V model. Now, once requirements are constructed into layers, traceability to the source code implementation can be achieved. In this slide here, you can see an example where the left-hand side has the system-level requirements. And it goes all the way down to the low-level requirements, which finally maps to the functional level. And this makes sure that each low-level requirement has been implemented. This traceability upstream goes all the way through each requirement level to the system level and tells us how the requirements are being implemented. And traceability also helps us to make sure that the effects of the requirements being changed or source code changes are being documented and so that they can be properly reviewed and managed. With the requirements traceability tools, It's really easy to see which requirements are not being implemented yet or implemented correctly. So you can see in this, all the ones that are highlighted with red are not being covered. And that's one thing we'll have to fix. Now, it's not required to do a review on traceability on each source code commit or every time requirements change. It's typically something that's done every once in a while against a review milestone. But one thing that can be done with every commit is checking for coding standards compliance. Coding standards are mandatory by functional safety standards. The good news is that there are a lot of standards to choose from, but then the question becomes which one to use. For example, we have Cert C, High Integrity C++, MISRA, AUTOSAR, etc. The bad news is that taking the time to understand each one and knowing which ones to use can be really time consuming, especially for the more non-technical people. If you're programming in C, the best standard to use would probably be MISRA C 2012. It's specifically designed to reduce the likelihood of introducing defects from using some of the more questionable or undefined behavior syntax in C. You can then supplement MISRA with style and documentation guidelines. But now MISRA also has some good suggestions for this. For programming in C++ 14, the AUTOSAR C++ 14 standard guidelines are probably the best reference for now. And one important thing to consider is that a very strict coding standard isn't something that you should just apply very later on. They should be used for new projects only or whenever you can as early as possible. If a coding standard is used with existing code that has a proven track record of not failing, then the benefits of using that coding standard could be outweighed because trying to make the code compliant could also introduce some bugs. Now, when checking for compliance, we have the option of doing it manually or by using the tool. Clearly, it makes a lot of sense to use a tool because it makes life easier for everyone. But since there are what's called undecidable rules, there's still a lot of manual checking that still needs to be done. Undecidable rules are rules that just cannot be checked completely through static code analysis. For example, one of MISRA's rules is a project shall not contain unreachable code. It sounds simple enough, but it's actually not completely possible to know whether there is or isn't any unreachable code without doing dynamic analysis or structural coverage and unit testing. And detecting bugs in your code is like getting fruit off of a tree. The low-hanging fruit can be picked easily and quickly, but the high-hanging fruit requires a lot more time and effort. So compilers often integrate MISRA checkers into their tools. And they work by checking the rules that are really simple and really quick to do and don't heavily impact compilation times. But as a result, they don't check for a lot of the rules, and in case there's any doubt, they're generally more optimistic, and that results in a lot of false negatives, meaning that it won't report on a lot of possible violations that it finds. With the heavyweight tool, though, a deeper analysis can be done on the code, but the cost of that is it's more time consuming. These kind of tools tend to be considered more pessimistic, and they just report on any possible violation that it can find. The idea is that it's better to be safe than sorry. And it probably sounds more frustrating to developers since now there's more things for them to fix, but really it's a good problem to have. And this usually happens with the more undecidable rules so that you can use it as a sign for where to look during manual reviews. So another thing that can be analyzed with tools is code complexity. If you take a look on the graph, at the graph on the right-hand side, that's a flow graph, and they show the control flow of a function as these nodes, which are the red circles. So anytime there's a branching statement, loop, or a function call, it'll show up as a node. And in this example, we have a flow graph for a function called remove last. By counting the number of regions, we can measure what's called the McCabe cyclomatic complexity, and in which case, for this function, is only 4. Now in this example here, we have the flow graph for a function in the 7-zip program. This function getOptimum has a cyclomatic complexity of 98. And as you can probably tell from the graph, it looks pretty complex. So you probably wouldn't want to try to understand, maintain, or test this code. And as a general rule of thumb, anything over 50 is considered to be complex and high-risk code. Here's an example of what happens when code is too complex. Earlier, I brought up the incident where certain cars from Toyota would unintentionally accelerate, and millions of cars had to be recalled, and there was a huge fine on top of that too. So the bar group did a study on the code that caused this and found that it was a classic case of spaghetti code. From doing a dynamic flow analysis, the 2005 Camry L4 or LE had over 11,000 variables, global variables, and that's not a small number at all, 11,000. The control flow analysis showed that there were 67 functions with a cyclomatic complexity of over 50. And the throttle angle function scored over 100. Again, anything with over 50 is considered to be really complex and high-risk code. And this is just one of those situations where poor software development and verification processes in the industry has caused deaths or serious injuries. But unfortunately, this isn't the only case. There are a lot of documented cases of vehicles failing to respond accordingly to life-threatening scenarios. So what's the best way to avoid this kind of scenario in the first place? Well, first you would have to define your definition of complexity, and it's usually based on an industry best practice. And a good place to start would probably be a cyclomatic complexity with a value of 15. Second, you have to be able to measure the cyclomatic complexity and then stick to it. Using a tool to automate this would probably be your best bet. Third, dealing with exceptions to this rule. Every now and then there's going to be a circumstance where it doesn't make sense or it's not even possible to follow every single guideline. And a reasonable software development process will have its way for dealing with this kind of situation. And then you just supplement this with guides on global data use, documentation practices, and other software metrics. Next, let's talk about data and control flow. Here you can see an example of what's called a call graph. It shows all the functions in your system as these boxes and also shows how they are all related to each other. Control coupling analysis is about analyzing the relationships between these different software components in your system. And it asks questions such as, has each software component been called when expected? And has each software component been called at least once during a full regression run? This is a really good way to find dead code. Data coupling analysis. This analyzes the reliance of a software component on data and the relationships between the data objects and the software components. So for example, let's consider a sensor that's reading data constantly from the outside world, and it's passing this data to many other different software components in the system. Now let's ask ourselves, has the data been written to global storage when it's expected to? Has the data been read by other software components when it's expected to be read and not before a write is complete? Has the data been appropriately sanitized and filtered before passing to other modules? An example here of sanitation, of data sanitation, would be the heartbleed bug that happened a few years ago, where code didn't check for inputs. To verify this, details of the data read and write It can be tracked through integration and unit testing and reviewed against requirements documentation. But all of this requires a collection of structural coverage data through dynamic analysis, which we're going to talk about. Structural coverage measures how much of the code under test has been executed, and it works by inserting probe points into your code and executing it. At a higher level, though, you can think of structural coverage as a way of providing evidence that you have a full test suite and that you're fully testing everything. So you can use it to show that the code that you tested, there's no runtime errors. And getting the most out of structural coverage requires requirements-based testing. And then it can be used as a way of highlighting potential gaps in requirements. So if all your tests are designed to cover at least one requirement, and you run all your tests and you get less than 100% structural coverage, it means that there's some potentially missing tests that you have to write, or requirements missing, or you have dead code. So here's an example of using a flow graph that's overlaid with structural coverage data, and you can see which parts of the function have yet to be executed by looking at the red nodes, the red sections. And also shows the conditions needed to execute these blocks of code. There are two main ways to gather and measure code coverage, and different industries go about this in different ways. So in DO-178C certification, the suggestion is for you to use an approach where as much testing and coverage should be obtained as possible at the highest level of tests. So what this means is that with DO-178, you should aim to get as much structural coverage from system and integration testing, but running lower level tests or unit tests can be a great way of filling in the gaps in structural coverage. On the other hand, in the automotive and medical industries, the focus is more on verifying software at the unit test level and functional level. So this usually means that you have a more complete unit test case suite. Structural coverage activities should be mainly performed at the unit test level, and the high level tests, the system tests and the integration tests, they should be used to verify functional behavior, make sure that your project, your code is working as expected. And generally speaking, the most cost-effective approach is to reduce the verification burden and obtain coverage at the highest level of functional testing possible. And some projects use coverage as a way of checking test effectiveness across the software within an environment that is different from the actual shipped device. So for example, executing on an Intel or AMD processor instead of running on embedded. So we all know that unit testing and integration testing is important and that it's required. However, unit tests and integration tests are meaningless unless they're run from within the same environment as the final system or shipped product. It's pretty difficult to get certification credit on tests run in a different environment, or even something that simulates the final environment. And it doesn't really make sense to. There's a lot of simulation and emulation tools out there, and they're great for development if the hardware, the real hardware, isn't available. But for software verification, the real hardware needs to be used. It's a requirement. And this means that you have to use the same compiler, processor, and hardware as the shipped product. But one issue is that in real-time systems, this can become a bit difficult since many testing techniques can have some very high performance overhead. Memory consumption, runtime performance, I/O mechanisms are also some other things you have to take into consideration if you have a real-time OS. So that's why it's important that testing technology can integrate with these technologies. Which brings us to why tool qualification is an important part of many industrial process standards. Tool call is where a tool goes through testing to provide evidence that it's functioning correctly for its intended use cases. For some standards and safety integration levels, or SILs, tool qualification efforts can be reduced by a lot if the tool is already pre-certified for safety. And a third-party organization like TÜV will audit the tool vendor companies such as LDRA and make sure that the tool's software development process is being followed correctly and guidelines are being followed, and that the tool is of high quality, and they produce reports and certificates. So this is a huge time saver for customers using these kinds of tools, since creating test cases and requirements documentation for third-party tools is really difficult and time-consuming. And often, for software tools, this qualification process requires software developers to work on it, which they could be working on something else instead, like the project at hand. So on the screen here, you can see that these are the two certificates, and typically they mean that for most functional safety standards, tool qual, it won't be required, such as for the LDRA tool suite. And LDRA goes through regular audits from the British Standards Institute, TÜV SAR and TÜV SÜD. TÜV SAR on the left, TÜV SÜD on the right. But for standards like DO 178C, tool qualification is going to be required regardless of the tool's vendor's claims anyways. So the tool qualification process goes a little something like this. First, the tool needs to be categorized generally and whether they can introduce a debugged or defect into the project, such as a compiler, and verification tools, which they don't introduce errors but can fail to detect them. Next, a confidence level can be identified, and then which will determine the process needed. And LDRA has deployed over 200 successful tool qualification support packages to assist customers with this. And finally, let's talk about compliance management. Compliance management is about collecting and combining documentation required to show compliance. For example, what are the the inputs to process, what defines a process, how are you implementing it, source code changes need to be documented, and this documentation will then need to be managed. And once appropriate processes are created, you can then establish a paper trail that shows all the ways that the human and the automated activities are connected. And then you can present that to certification authorities. So nowadays, with the increasing demand for functional safety, a lot of manufacturers will find that they need to become compliant with functional safety standards. And hopefully this will shine some light on the idea of functional safety and security. Thank you everyone for your time and for listening. If you have any questions, feel free to ask. And if you want more information, feel free to contact us here. And thank you to QtCon.
Absolutely. Okay, well, thank you for the informative session, Tim. And as we're getting close to the end of the session and the end of the day, please note that you can find the link to send us some feedback or join the next day's live sessions via the page that you see here. So the www.qt.io/thank-you survey. Tomorrow, you can also join the same link that you accessed in order to get to the live agenda in the live event portal. You can also give us your feedback at each of those sessions by completing the survey, and we look forward to your feedback, positive or negative. You can also join, the Qt Professional Services on the live chat on the live event portal right now, if you have any additional questions. And now you can, as you can see in the slides, you can also follow us in our social media channels. So there's Twitter, Facebook, LinkedIn, and YouTube. And you can also contact us at any time at those addresses, or download Qt at qt.io download. Okay, and now let's dedicate some time for a few minutes of interactive Q&A, and we'll pass the mic back over to you, Tim.
Thanks, Iris. Should I stop sharing?
You can continue to share, but move the window on the side so it's not covering the text or.
Okay. Does using signal slots or QML have an effect on how accurate code analysis tools are? No, they shouldn't affect it at all. How does this integrate with any development environments? Can you give me an example of your development environment, and I'll try my best to answer. How does your tool help trace requirements to validation? So we have a tool called TB Manager, and it's essentially, it ties in all the tools that does static analysis, dynamic analysis, and unit testing. And you import your requirements from a tool such as Doors or Polarian, and then you can easily set up the links between the unit tests, and then you can also combine it with the test results that you get, the analysis results. Is this tool something that can be integrated into continuous integration tools? Yes. A lot of our customers actually use it with Jenkins and Bamboo. Can it be used to gate merge requests or builds? Yes, you can. I have seen customers set it up so that if it doesn't pass analysis or reach a certain percentage of the tests, then it refuses a commit. And I'm sure it can be configured to do other things too. Does this integrate with requirements management tools? Yes, we have quite a few integrations with tools. If you can recall from the previous slides, we have integrations with Codebeamer, Jama, Polarian, Doors, just to name a few.
Okay, are there any additional, oh, we have another question.
If requirements are being collected in Microsoft Excel, can your tool be used? Yeah, we can parse Excel sheets and using regular expressions and just create the requirements management. Are there demos or evals? Yes, we do demos and evals. If you would like to, oops, sorry. If you would like to request a eval, just go to LDRA.com and you can find out more.
I think that was a good segue to point them over to your page. And it is the end of our first day of the CUTE Virtual TechCon. Thank you again, Tim, for graciously joining us and contributing to the CUTE Virtual TechCon. If anyone has any more additional questions, please do go to LDRA.com or access the CUTE Virtual TechCon page and connect with the professional services team or any of your account managers.
All right, thank you, Iris.
Thank you.